Okay, so yeah, I think we are now live once again. Welcome back, everybody, to another edition of Quarantine Thermo. We're very excited this week to be able to welcome Professor Heiner Linke, who you see in front of you. Okay, I guess many of you are very familiar with his work. He's been doing pioneering kind of theoretical and now, and experimental work on thermoelectric energy conversion, and that's what he's going to be telling us about today. So before I hand over to Heiner, I'll just kind of briefly recap the format of this talk in case we have any new people who haven't seen these talks before. Hold on, my computer seems to have frozen, so this is no good. Here we go. Okay, we're back. Sorry about that. So yeah, one of the things that everyone should realize is that technical problems are unfortunately par for the course as part of this series. So we'll deal with them as they come along. But assuming we don't have any technical problems, basically Heiner is going to speak uninterrupted for however long he wants, and then at the end of the talk we'll have a question and answer session. So anyone who has any questions during the talk or after the talk, please just feel free to write them in the YouTube chat window, and I'll relay them to Heiner at the end, and he can answer them for you. So yeah, without further ado, I'll hand over to Heiner. He's going to tell us about efficient thermal to electric energy conversion in nanowires. Please go ahead, so you can share your screen.
Thank you so much for having me, and I try to share my screen here. So can you see my screen okay?
That looks good. Yeah, perfect.
Perfect. And I expect the talk itself to take about 35, 40 minutes. Does that sound okay? Yeah, perfect. Okay, well then, let me start. I will talk about thermal to electric energy conversion in nanowires, but it's the sort of thermodynamic type, where I will make this very clear as we go along. I will really talk only about electronic heat. So for those of you who know about thermoelectrics, where you know that heat conduction in the phonons is a major part of the performance of a material, I will relate to that a couple of times, but it will not be considered in this talk at all. So instead, we are interested in the heat stored in electrons in a system and how to harvest that. And with this first slide, I will try to sort of introduce the language that I will use throughout, which I think is probably familiar to many of you. That means I will basically consider throughout the talk, I will consider two electron reservoirs. So this will, in my talk, mostly be the ends of a nanowire, but could also be two-dimensional electron gases or something. With two different temperatures, a hot one and a cold one. They will be separated by, there will be a voltage between them that is important to be able to do work. So in general, we will have a higher electrochemical potential on the cold side and a lower on the hot side. And the whole idea is to get the warm electrons go against the voltage, for example, to charge a battery. And to do that, we need to put something in the middle. There's some kind of energy filter in the middle. And basically, most of this talk is about what to choose for this energy filter to make the process as efficient and effective as possible, and both from a theory side and experimental side. So this is then the outline of my talk. I will give a little bit of theory background. Some of this work is approaching 15, 20 years old. But this is sort of has been the basis for this work for a long time now for me. So I give that introduction as sort of a theory introduction. Right. Then there will be an experimental part where I report or tell you about experiments that were published 1.5 years ago or so, where we managed to achieve highly efficient thermoelectric energy conversion using a quantum dot. And then I will work on talk about things we are working on now, namely to apply this at least to understand the fundamentals of hot carrier solar cells. So I will explain what that is, and you will see then, I think, that this is clearly the application for this type of system. At least that's from my perspective. So this is my outline. A little bit of theory background. So this is work we published a long time ago. We came then from really sort of fundamental ratchet experiments. We, as my first graduate student, Tammy Humphrey and me, and this is really a lot of it is her work and was her PhD work, everything also. We were interested just very fundamentally, not knowing anything about thermoelectrics at the time. We were just interested in the question, if you have a hot bath and a cold bath with the voltage in between, is it actually possible to put an electron from hot to cold and run this system at Carnot efficiency? At the time, that wasn't specifically answered like that question. But if you draw it like this, it's boiled simply down, or the way we boiled it down was to simply say, can we take an electron from the hot side to the cold side at any given energy, epsilon, in such a way that the entropy of the system doesn't increase, meaning you do it reversibly. And once you phrase it like that, it becomes a very simple problem. You can write down the entropy change on the hot side, which has to do with the energy that you have relative to the electrochemical potential. So that's basically the heat divided by the temperature. And you will then remove some entropy from one side, add some entropy to the other side, and you need to look, can this be zero? And it turns out, yes, there is such a point for every given system with two different temperatures and one voltage. There will be one energy where you in fact can do this trick without changing the entropy of the system. There's only one energy, so we call this energy-specific equilibrium, because if you put an energy filter at this position, which turns out to be simply the point where the two Fermi-Dirac distributions on the hot side and the cold side where they cross. If you did a delta function ideal filter at that position, allow electron flow at that energy, but at no other energy, the system would behave as if in equilibrium. There would be no net heat flow, no net charge flow, because there is no entropy change associated with electron exchange at that energy. It turns out that this insight had been around, unbeknownst to us at that time, maybe not phrased in those words, but for the general case of a thermoelectric transport system, Gerald Mahan and his co-worker had already found this as an optimization problem, that a delta-shaped transport distribution in fact maximizes the thermoelectric properties. So what we could add to this was that it in fact is then the Carnot efficiency that you can work at. And it turns out, so if you now think of an energy filter that has a little opening, so a finite width somewhere, then if you make that finite width a delta function, you have a system that doesn't do anything. It's as an equilibrium, so that's a perfectly Carnot efficient system, will not do anything. If you want to produce some work, you need to open up your gap above that magic energy. If you can also choose to open it up below, and then you get a refrigerator, and always at a loss of efficiency pays for the increase in power. So this is sort of the basis of pretty much everything in this talk. There's one addition, which I'm sure many of you are familiar with. The Carnot efficiency is always associated with reversible operation and therefore zero power output. What is much more interesting if you want to actually apply this to something is how much efficiency can you get at finite power. And specifically the maximum power case is then associated with the Curzon-Ahlborn efficiency, which is not a limit, it's sort of a guideline. Depending on the system, you can find small deviations from this, but in particular, if you go into the nonlinear regime, there can be also stronger deviations. But for a linear case, you can derive this as a good approximation of the efficiency you can expect at maximum power for a heat engine. And that turns out to be approximately half of the Curzon-Ahlborn efficiency. This was shown for the specific case of a transport through a single energy level, for example, a quantum dot, which we will get to in a moment, by Esposito, Lindenberg, and the late Van den Broek, who derived this and showed that also a quantum dot behaves according to this. In this case, maximum power is defined as you have a delta function resonance, which doesn't give you much power. But then you move that around and you find the optimal spot. Then you can show that you operate near this Curzon-Ahlborn efficiency. Yeah, this is my background. And now to an experiment that we succeeded with about 2 years ago, which literally took me and my group in various efforts now and then with restarts and new attempts more than 10 years to realize. So I'm very proud of this result. And we'll try to highlight the key contributions here on the way. So I will save you all the things that didn't work and just point a few things that were important to make this work. So one of them is to have a quantum dot that is really well defined. And the system we chose, which is sort of natural for this problem in the end, is a nanowire. Because it has this one-dimensional structure, you can imagine if you want to have a heat gradient, having one free dimension is not a bad start. And then you need well-defined energy barriers to define a quantum dot. So here's a system that was developed in the early part of sort of the 2000s. In this case, it's 3 energy barriers. Indium arsenide is a system with a small band gap. Indium phosphide is a material with a big band gap. The CBE technique allows you to make very sharp interfaces between the two materials, really sort of atomic layers, which gives you very sharp bumps in the conduction band. And you can see that you can build a quantum dot out of this. So I show this to you in a moment. So this is one ingredient. This was developed to perfection in the last 10 years or so, I would say, or maybe a bit more. The other thing we needed was the ability to heat our system, to apply a heat gradient in particular, while maintaining a low temperature. So we want to use quantum dot physics, which basically means you want to hang around 1 Kelvin, maybe up to 4 Kelvin, 10 at the most, otherwise you lose your quantum dot physics. Now, people have looked quite a bit at nanowires in thermoelectrics for quite some time. And here is a device that people typically use. So you can faintly see a nanowire here. If you can see it, I can see it. Then you have a 4-point contact system at either end of the nanowire. So these are your electric probes to measure thermal voltage, for example. Everything sits on a surface. Here you have a cross-section of that part. And then you put a heater system somewhere nearby so that you can heat from one side. And this sets up a heat gradient that looks something like this. You deposit a lot of heat into the substrate. Some of that spreads out to the side, and the nanowire sits on some amount of heat gradient then. This works great for experiments from room temperature down to 40 Kelvin or so. But then you cannot really get much below, because the only way to get a heat gradient is to really heat everything. So you cannot really work at near 0 Kelvin and have a heat gradient with the system. You have to choose one or the other. So one system, an important breakthrough was that we in our group, Jan Gluschke, a master student at the time, developed a system where we put the heater not next to the nanowire, but on top of the ohmic contacts. So again, there's a nanowire here. You have 2 sets of contacts. Both of them allow for 4-point measurements. Then you put on top of the contacts, you put an oxide layer, so to insulate, electric insulating, and then you put another circuit straight on top. So if I heat now, I heat very locally the ohmic contact and thereby the electrons in the metal, which then will heat the electrons in the nanowire very locally. And that allows us, so here sort of characterization experiments. The first one is done at room temperature, where we were able to measure the temperature on the hot side and the cold side of the nanowire as a function of heating power. And you can see the hot side really gets hotter, starting from room temperature, the cold side hardly. And this gets even better if you go to low temperature, because then you reduce electron-phonon coupling, and the phonons as a heat gradient mediator sort of go away gradually. And it turns out at low temperature, you can really, to a very good degree, heat the hot side of a nanowire, and a micron or so, or even just a few hundred nanometers away, it stays cold, which then is a prerequisite to be able to do a heat gradient at low temperature. So this is sort of the short version of this 10-year voyage. And the experiment that I can then report about was done by Artis Svilans, an experimental student in my group who worked very closely with a theory student who was Martin Josephson, who I will show in a moment. So here's the nanowire with these 2 energy barriers grown by CBE, which basically sets up a system that in very good approximation looks like this. You have individual energy levels that are quantized by Coulomb interaction primarily. You have the ability with our heater systems, we can heat one side while to a good degree keeping the other side cold. The quantum dot also acts as a thermal insulator between the two electron baths, so you can maintain that temperature gradient. Then we hook everything up to a circuit so that we are able to measure the current driven by that delta T across the quantum dot. And we actually push it through an external resistor. So I will show you the measurements I will show you are the actual electric power produced by the quantum dot measured across a real life up to a mega ohm resistor on the outside. So this is really doing work in this sense. So this load resistor here will come in as an important part of the load matching in this story. The other part that we needed was, so this dot that we used in the end was well selected. They had to look for one that really behaves well according to theory. And according to theory also includes an extra effort to go to higher order theory, because we wanted to really account for every detail of the behavior of the quantum dot. And that was done by Martin Josephson, who really developed the theory to higher order to be able to show everything. The reason is the following. We can measure the power produced by the quantum dot, but to get an efficiency, we also need the heat flow through the quantum dot, and we're not able to measure that. So the only game plan we had then was to measure the power and then have a quantum dot that is so well behaved and so clearly in agreement with theory that people and we ourselves will be able to believe the calculated heat current and use that for our efficiency. So that's why we wanted this perfectly behaved quantum dot and a perfectly matching theory. So to show you how well this matches, these are conductance peaks. So on the left hand, you have what we call a stability diagram. So basically we have we measure conductance through the quantum dot as a function of two voltages, an external bias voltage that we can control and a gate voltage that basically sets where our chemical potential is relative to the conducting states of the quantum dot. And if you look at zero bias voltage across here, then you cross points where the quantum dot conducts. And a cross section through here would be such a graph of this. So the black line is the measurement, that's the conductance as a function of gate voltage. And then, sorry, the black line is theory and the red dots are experiment. And you can see that this fits very well. From these data, we can also extract the coupling strength of the quantum dot to the baths. So we are assuming symmetric barriers and then can get a gamma of the tunnel coupling to the baths. This is done at two different temperatures, and the fact that you get similar gammas for two different temperatures is one nice confirmation. Then on the bottom left here, you already have thermoelectric measurements. So this is now applying a temperature difference between the hot side and the cold side, tuning with the gate voltage, tuning the Fermi energy past this resonance. And then you see this very characteristic sign change in the thermoelectric current that is produced, because either you have the Fermi energy below the resonance or above the resonance, and then you get either hole or electron transport, or electrons to the left or to the right, depending on how you choose to see it. And again, the red dots are measurements. The black line is now a fit to the measurement using the gammas that we have determined already as an input parameter, but having the temperature on the cold side and the hot side as fit parameters. So from this fit, we get also a delta T. And on the bottom right panel here, you have the extracted temperatures on the hot side and the cold side based on these fits that you see here. So that gives us a delta T. And now we can, this is a different type of plotting the current. So this is now plotted as a power already. We know our voltage, so from the current, we can easily calculate the power. And you can see that the quantum dot produces finite power on either side of this resonance. More on one than on the other. This has to do with spin degeneracy. So this is nicely reproduced by the model as well. The dots are again measurement. The black line is the corresponding theory prediction. The blue line is the calculated associated thermal current through this resonance. So we cannot measure that, we can only predict it, and saying that the quantum dot behaves nicely according to theory, believe that this thermal current is also true. From the ratio of the electric power produced and the thermal current that we expect, we can then calculate an efficiency and make these nice loopy graphs here, where in each quadrant here, you have on the one side the measured power, on the other axis the calculated efficiency for each data point here. So for example, the red crowd, which is sort of climbing up to the power peak, each data point gives you a power and an efficiency value climbing up to maximum power with increasing efficiency. And then as you go closer to the resonance, your power decreases again, efficiency kind of increases, and then it gets very noisy. So this was sort of a disappointment because we had hoped to explore this maximum efficiency regime, but clearly with these data points, we cannot extract anything. But what we did instead is we did these loopy graphs for different load resistances. So it's a form of load matching that we do here, in this case, sort of by trial and error. And then we said, fine, we cannot really extract anything about the maximum efficiency regime, but the maximum power points for each load resistance, so there are different behavior for each load resistance. The maximum power points we can actually extract quite reliably from this. So extracting now for each load resistance, the maximum power that we can get and the efficiency at that maximum power, we can then sort of do summary loop graphs. So this is for two different heat settings. Let's look at the red one first. That's the higher temperature difference. We can, for each setting of load resistances, we can then extract a bunch in multiple experiments. We can extract power and efficiency and find then there are load resistance that give us higher power and there are load resistances that give us higher efficiency. And these follow quite nicely then a loop graph where the line again is the theory prediction and the dots are experiment. And we also marked where the expected Curzon-Ahlborn efficiency is for the system and find that the maximum power is very nicely reproduced at the expected value of Curzon-Ahlborn efficiency of close to a bit more than 50%. And depending a little bit on how you choose to see this, we can extract efficiencies above 70% of Carnot efficiency. So this is basically what we had set out to do. We wanted to show that with a quantum dot, it's indeed possible to convert heat into electricity. And now it's important that I emphasize for the electronic system, we are totally ignoring the fact that there's also phonons. But for the electronic system, we can indeed, even in practice, convert electricity into heat into electricity at even with finite power output at 70% or maybe even a bit above from Carnot efficiency, which is as good, or I would say in most cases better than macroscopic optimized heat engines perform. So that was very nice. A little comment here, because quantum dots are often seen, because of this work here and others, quantum dots are seen as the optimal system for thermal to electric conversion. But there's a number of things one needs to say about this. One is we pushed this system to sort of, we optimized the coupling to the reservoir such that we would get a decent signal, so we couldn't have too low coupling, but still as low as we could to get this delta function like resonance. And that allows us to get relatively high efficiency. Now, the problem with quantum dots is if you open up, if you increase the coupling and you make your resonance broader so that you get more power out, the performance actually decays very quickly. So here sort of, it's just a very simple Landau type model where we just sort of estimate what is the power and efficiency you can get for different widths of this resonance, where we tried to be sort of in this corner down here. We tried to have an as narrow as we can resonance. We even went to slightly higher temperature to decrease our resonance width compared to KT. And we lived down here. We were able to get some 70% of Carnot, meaning we got very little power. Now, you can get more power by opening up your resonances by making the coupling stronger, but you lose efficiency very, very quickly. So a quantum, because these tails, so in particular the low energy tail here, is really leaky for cold electrons that then go back. So the only way then you can keep your power high is to move the resonance away from this ideal situation, and you lose efficiency very quickly to get the power. So quantum dots are not actually a great system for power production at high efficiency. We really just pushed it into one corner of the system. You can play with this for different systems, and we'll find that a one-dimensional system like a perfect or sort of an ideal quantum wire with a barrier in the middle is actually a much better compromise. And this is what we will use later in some of the other experiments. For a number of reasons, I can go into this maybe in the discussion session. The message here right now is that quantum dots are really good for fundamental things, but not so good for applications. So if you sort of push this, you can find that at maximum power, a quantum dot where you actually maximize power by opening up the resonance only gives you 17% of Carnot, even in the ideal case, ignoring phonons. So this is lousy. Versus a thermonic barrier in 1D actually gives you more than twice of that. So this is what we use later. You can actually play with this a little bit. So these were sort of the transmission resonances you get for free. You can also dream of what would be my transmission resonances if I could choose. And it turns out if you want to build your own transmission function, you would want to build one that basically blocks electrons at low energies to zero and has a very sharp turn on. That's important. And then you want to have a finite width to get power. But what that shape then looks like turns out to be less important. So you could have a square shape or some kind of tail or something. The important bit is this sharp turnout from zero to high quickly. And this is just something I just want to highlight. A graduate student here in the department who heard me say something like this and then came up with this idea of actually using interference effects to model something like that. When he did the theory first for a quantum dot and then realized that quantum dots are difficult to use because you need low temperatures, and then did the same physics with a molecule that you in principle could do at room temperature, and showed if you can set up interference between two different states at two different energies with different parity, you can then achieve destructive interference for low energies, then get the sharp turn on and have a nice open system here where you can do some work. And that turns out to indeed, in theory, perform better than a quantum dot at maximum power. So this is very nice. There's also some progress towards realizing this in experiment with designed molecules, which would then actually be room temperature experiments with designed quantum interference effects to improve thermoelectrics. So that's quite interesting. So the takeaway message in terms of what I really want to say here is, yes, we can produce electricity from warm electrons with high efficiency, but it's not something that comes for free. We are talking about very specifically chosen working points that depend on T, delta T, and delta V, so the voltage difference. You also need to match the load, so you cannot just use any load for any given quantum dot. They need to be matched. And if you really want this to push to higher power, you really need to think of the shape of the transmission function. So this is not, it's possible to do this, but this is not something you get for free. Sometimes people do experiments with thermoelectric materials where they sort of put some quantum dots in there and hope for something magic to happen, but it doesn't happen, not just like that. And now I would like to switch to something entirely different, because I want to interest you, hopefully, in the fact that so basically, if in our quantum dot experiment we would include the fact in the analysis, the fact that of course we heat one side, we keep the other side cold, there's of course a massive phonon flow carrying heat from hot to cold all the time. That's a pure loss. If we included that into our efficiency analysis, we would come out with lousy values, like way below 1%. So You can ask, well, is there actually any value in any of this? And what I would like now to point out, yes, because there is actually an application where you are specifically interested in harvesting heat from electrons that are not in equilibrium with the phonons, where you exactly want to do this. You want to harvest this non-equilibrium energy, and you don't have to care about the phonons. And that application is hot carrier solar cells. So let me give you first a brief introduction to what people mean by this. In the top here, I have the band diagram of a simple, what a commercial silicon solar cell would look like. So you have a p-type struct end, an n-type end, and then in between, typically an intrinsic part, so a nominally undoped part, because you want to have a certain volume to absorb light in. And then there's this key characteristic of a semiconductor, which is the band gap, which becomes really important here, because down here there's a diagram which tells you about losses and gains and performance of a solar cell as a function of band gap, which I'd now try to explain very roughly. So what you do in a solar cell is you have this system, you send in light, you excite an electron from the valence band to the conduction band, and that gives an electron-hole pair. And initially, in general, this photon has an energy that's in general larger than the band gap. If it's smaller than the band gap, it goes straight through, it doesn't do anything. But most photons that get absorbed will have an energy larger than the band gap, meaning you get kinetic energy of the electron and the hole to start with. Now, in a normal solar cell, you don't use this kinetic energy. What happens now is that the electron diffuses around until it discovers it can fall down here. The hole also will diffuse around and then discover it can bubble up here. And then you can declare success. You have separated the electron and the hole. If you close the current, you can drive a current and keep this going. But the key point is you have lost this kinetic energy that they had in the beginning. And that loss is important because if you now choose your material to do such a single junction solar cell, you have two bad choices. You can either use a large band gap and then most of your photons will go straight through, or you can use a small band gap, then you catch most of the photons, but most of your electrons and hole pairs have lots of kinetic energy, all of this thermal energy here that gets lost. So what you can do with a single junction cell, you can try to balance those two bad things, so the transmission and the thermal losses, and find you get the most power out at around 1 point something electron volts. And then you can either go for a cheap, abundant material, that's silicon, this is down here somewhere, or for some more expensive, which is gallium arsenide, which is up here, and then you make your single junction solar cell. Now, there's one way around this, which is to make triple junction solar cells. Sorry, I'm just trying to get there. I need to go through this again. In triple junction solar cells, people make 3 of them on top of one another, each of them optimized for one part of the solar spectrum. And then you can indeed get to surprisingly high efficiencies, very close to the thermodynamic ideal. This works very well, it's also very expensive. So this is one way of dealing with this. The other way would be to play a smart game with the equilibration process and say, well, I don't have to wait until my electron hole pairs are relaxed or have thermalized and given off all of their energy. If I think of this on a time scale, so this is now imagining I come in with a light pulse into an equilibrium system. The system to start with has some small concentration of electrons and holes. And now I come in with my light pulse and I create a bunch of holes and electrons at a non-equilibrium energy. Now, if you leave the system alone, two things will happen very quickly. The first is you get equilibration of this kinetic energy among the electrons and holes. So you get electrons and holes with a high temperature. And then they will cool to the lattice temperature. So the first process happens within a picosecond or so, the latter within a nano microsecond something. Now, normal solar cells work in this end down here. They work with the equilibrated electron and holes, and you simply have those thermal losses. A hot carrier solar cell, the idea would be, well, can we harvest this heat that's stored in the electrons and holes before they give it off to the lattice? And that's now important because from a thermoelectric perspective, we are now talking about heat that is stored in the electronic system And phonon losses in the heat flow do not need to be considered. If the heat goes to the phonons, we consider it lost anyway. So we only talk, the heat that we talk about as a resource is the one that is not talking to the phonons. So we have this short time window to do something. And then what we need is the type of thermoelectric system that I discussed, where we can convert heat into electricity at high efficiency, and we don't have to care about phonons. So a system that you could sort of dream of then in the language of this talk would be, you imagine some kind of, this is sort of a magic structure that doesn't really exist, but this is sort of a thought model. You would have an absorber region where you absorb your light, which has a small band gap, because you want to catch all the photons now. And you absorb photons of high energy in average, which gives you a hot electron bath and a hot cold bath. And then, of course, there's a surrounding world that's cold. This is to the left and to the right. We imagine an electron collector here, a whole cold collector here. And you can guess why I have a double barrier structure, because really now you have a system where you would like to set up a thermoelectric system for the electrons and one for the holes down here. And this is what we know how to do at this point. In addition to that, you have the quasi-Fermi level splitting. So this is the way people describe solar cells. They say if I have a non-equilibrium concentration of electrons, because I have generated electron hole pairs, I describe this with one Fermi energy that's now high for the electrons and one for the holes. So you have a quasi-Fermi level splitting. That delta mu is the best voltage a solar cell can produce. So you now have three resources. You have the delta mu from the solar cell, plus a thermoelectric system for the electrons, plus one for the holes, which you would want to use optimally if you can. So once I learned about these things from a graduate student called Steve Limpert, he will be on the slide just in a moment. We set up just a basic system to see, so this is sort of the simplest model we could come up with to see, could you actually run this thing reversibly, or is the system overdetermined somewhere? So we said the minimum system we would need is a hot electrons system and a cold electron system, a hot hole system and a cold hole system. And we want to operate this at finite quasi-Fermi level splitting, meaning under illumination while producing or maintaining a high electron hole concentration. And then clearly we would want to have some kind of energy filter for the electrons and one for the holes. And now the question is, can we send in a photon, create an electron hole pair, separate the electron hole pair, and all of that reversibly without losing, creating entropy in the separation process? The short message is, yes, you can do this. It's sort of the same problem as before, except that you now have 4 terms instead of 2. And indeed, for every given setting, there's again one situation where the entropy generation can be made to be 0, which turns out to only depend on the energy distance between the 2 filters that you end up using, the Fermi level splitting that you have, that's basically a question of light intensity, and the 2 temperatures that you set up in steady state. So it can be done in principle, at least there's nothing fundamental that prevents us from that. You can also play with these equations a little bit and say, okay, once we instead of setting the entropy generation to 0, we just let it be some value. So we allow some entropy generation. We know that is necessary if you want to extract power. And then you can look for the voltage that you can produce. And then it turns out the open circuit voltage is now given by that of an ideal solar cell, reduced by whatever entropy you produce. So this is normal for a solar cell, these 2 terms, but now plus a value that's given by your Carnot efficient energy conversion process. So we can increase the open circuit voltage beyond that of a normal solar cell by using this extra resource. And the important message from this analysis is just that there's nothing fundamental that speaks against it. There's many practical things to worry about, but nothing, not this fundamental question at least. So we have played with this experimentally a bit. I tried to go through this fairly quickly now. So you would now, to do this, you would want to have a system like this. You would want to have a one-dimensional structure where you can sort of have an in and out somehow. So we use our nanowires again. You would want to have an energy filter for the reasons that I explained before. We don't worry about quantum dots here. We just go for an energy barrier, which is actually a pretty good approximation for high power and high efficiency in a one-dimensional system. And then we would want to be able to control the light absorption such that we excite electron hole pairs on one side of the energy filter, but not on the other side. Because we want, in this case, we say we just ignore the holes. The holes get relatively little kinetic energy. We want them to stay behind on this side, but we want the electrons to be filtered across here so that we can separate them and then generate a thermionic voltage. And the first thing we did was to just try this without much control. So we just took a nanowire with such a barrier in the middle, slapped contacts on it, and shone light on it. And we got lucky in this case. This was maybe not supposed to work, but it did. It turns out that there's always some asymmetry. You absorb more light on one side of the barrier than on the other. This can be plasmonic effects at the contacts. That can be how light interacts with the nanowire. But it's actually the more commonplace, it turns out, is that you absorb by chance, in this case, more light on one side of the barrier than on the other. And at first attempt, we got a solar cell to work this way. So this is now IV curves where, let me go straight to this. So if you measure a dark current, then you see basically no current up to pretty significant voltages because you need to overcome this large energy barrier in the middle. So up to 250 millivolts, you don't see any current at all, basically. But if you turn on the light, then indeed you see a current happening that doesn't go through zero, meaning you have power production in this corner here. We plotted in comparison the theoretical limit if this was a p-n junction. So the theoretical limit for a normal single junction solar cell is the Shockley-Queisser limit. And it turns out two things here. We get much less current than one would, in the ideal case, hope for. The system is not at all optimized. So this is a comparison. We have about only 10% or less of the current than one could hope for. But we have a higher open circuit voltage at first attempt. So we have a open circuit voltage that's higher than the thermodynamic limit for a normal p-n junction cell. So this is this extra oomph we get from using a thermionic system here. So it's not a good solar cell, but it has at least the hallmark of something interesting happening here. One can understand this voltage that we get actually very simple. So if we do a very simple estimate of, if we simply assume we have hot electrons here and cold electrons here, and there's a thermionic barrier in the middle, then what temperature difference would that voltage correspond to that we get? And that's a temperature difference at 170 Kelvin under illumination. And that is very reasonable. This is what people see in photoluminescence experiments as well. If you blast light onto a nano or on such a system, the carriers will be hot on average as a steady state. So this is actually within expectation. Interesting is that this effect is enhanced in nanowires because the cooling process is hampered probably by phonon bottleneck type things. But yeah, so this sort of checks out. We have done two things in the meantime to sort of pin down what we think is happening is actually happening. So a student, Jonathan Fast, did electron beam induced current experiments. This is how this works. So you take a nanowire with a barrier, put contacts on them so you can draw a current. And then instead of light, in this case, we use the electron beam of an electron microscope. So this is basically a brute force experiments. You blast electrons with kilovolt voltages, so huge compared to light, 1,000 times more than photons, which also create electron hole pairs in some cascade of processes. So it's not pretty, but the advantage is you can do it highly localized with a very, you know exactly where on the nanowire you are. So we create electron hole pairs somewhere and check what current we get out. And the current you get out as a function of position. So you scan the electron beam along here and then check how much current do I get. Shows very nicely what happens at the barrier. If you put electron hole pairs close to the barrier, you get current in one direction. if you put them on the other side of the barrier, get current in the other direction. So this is consistent with electrons jumping over the barrier, just what we had in mind. You can, even with a very simple model, sort of assuming some kind of exponential decay of the hot carriers, you can extract them, you can fit this and extract some value of effective relaxation length, which turns out to land around 100 nanometers. With this experiment, which uses huge energy to create electron hole pairs. So the value itself is not that important. It just means that we can confirm that the process works the way we had imagined. This was important because people who know something about contacts and Schottky barriers that can happen at contacts were worried that maybe everything we see actually happens at the contacts. It's just some dirt effect. But that's clearly not the case. We don't see any current generation at the contacts at all happening around the barrier. We know that our barrier is there. The other thing you would like to do is to do this with light and actually control where the light is absorbed, not just hope that symmetry is broken somehow, but actually control light absorption. This can be done with such plasmonic elements. So you use two metal structures that are separated by about 50 nanometers or so, you can get strong light and electric field enhancement in this gap. So when you shine light on it, the light intensity will be strongly enhanced between these. And if you try to put them close to the barrier, which my student Yu Chen, she's now a postdoc in Copenhagen, succeeded with, then you can actually see what happens if you absorb light close to such a barrier. And she did that here. She showed very nicely that she can actually absorb light in this way. She did the same experiment before and after putting on the plasmonic element, so that's very nice. But the other very cool thing she did then was to play with the light wavelength she uses. So she can either use a light wavelength that would put electrons above the barrier, where they in principle can ballistically, without any thermionics, just fly across the barrier. Or she can use a light wavelength that puts electrons into the conduction band and heats the electrons in the conduction band, but relies on thermal emission through that thermal tail here. And then very nicely showed that as a function of power, she gets two distinct behaviors. In one case, she gets a linear behavior, meaning if you put more electrons up there, more of them fly over the barrier. So that's consistent with ballistic extraction. The other case is if you heat more, you get a bigger tail, but non-linearly so. So this is consistent with thermionic power generation, the way I described it before. So she showed really nicely that we can have control over this and can actually learn how to extract, how to play with these different processes. Now we have some ideas how to go from here to something. The quantum efficiency right now is really low. We expect that we actually extract between 1 and 10% of the electrons that we excite. This is also the reason why we were so low in current. So now with playing with multiple barriers and so on, we hope to increase that and get to much nicer quantum efficiencies. But with this, I would like to end and thank in particular the students. This is sort of the recent generation of students. Tammy Humphrey, of course, who did the theory in the beginning, but Artis and Martin are the theory and experiment pair who made the quantum dot heat engine work, really in teamwork. Stephen Limper taught me about hot carrier solar cells, and Iru and Jonathan did these experiments in the end with EBIC and plasmonic elements. And that brings me to the end, and I'll be very happy to answer questions.
Thank you very much, Heiner. That was a fantastic talk, very clear. So yeah, we have time for questions, of course. So I'll just bring my video back in. Okay, I think our group have a ton of questions for you anyway. So, but anyone who has anyone else in the audience who has any questions, I'll just remind you, please write them in the YouTube chat window. So I'll start off with a question from John Gould, who was asking. This was around the point where you were showing the quantum dot heat engine. So he was asking, can power fluctuations be measured as a function of efficiency?
Very good question. We are working on that. So we haven't done it yet. We hope to be able to do so. Our initial analysis says it should or might be possible to in fact get that, yes.
Okay, because we're very interested in that. I
Mm.
mean, we and many other people are very interested in the thermodynamics of fluctuations. As you may know, this is
Yes. Yeah.
becoming a very big
Yeah.
topic in the field. I mean, what
Yeah.
would be the limitations there? Is it just about the fact that the fluctuations are small, so it's hard, or
Yeah, it's the magnitude and frequency range, how much you can get it quantitatively out of it. But we have identified this as the next important thing to do in the quantum dot thing, and
Mhm.
we are working on it. So we think it's worth trying. So hopefully we can report something in a year or so.
Okay, great. Well, we look
Yep.
forward to seeing that.
Yep.
So John had another question, which was actually about probably an even harder measurement. So I'll just read you his words verbatim. He says, "Also, I am always impressed by the experimental progress, but it's always disappointing that heat cannot be directly measured. Is there
Mm.
any hope, even in the distant future, of a measurement of heat?"
So there are some, I mean, if you look in the field as a whole, there is some very impressive process. So people have developed scanning probe methods that get down to very small temperature differences that they can measure even locally.
Hmm.
There are also experiments mostly in the quantum Hall regime where you sort of play with edge states, and in that case can set up very controlled experiments where they have measured heat flows as low as we would need it here.
Hmm.
But to bring everything together is, I mean, I would say people have made so much progress that I absolutely don't want to rule out that somebody can do it, but I don't think it will be us. It will be somebody else. So one challenge is that for these thermoelectric experiments in particular, you want to leave so the voltage and the current need to be able to respond freely to the temperature difference. So you cannot try to control either of them, which typically is needed in these experiments that I talked about, where for example, you try to keep one quantity constant and then measure how much heating can I do before it changes, or set up some kind of balance that usually requires that you control either voltage or current. I think that's one of the challenges. But the progress has been amazing, and people can do things that I 5 years would have believed would be possible to do. So I think there's hope, but don't hope it from us.
Okay, so never say
Somebody
never.
else.
Yeah, but thanks. That's very interesting. So, okay, so we have a question from Archak Pokayasta, who's also in our group. So it's us just dominating the questions now. But so he says, how are the temperatures of the local hot and cold baths of the quantum dot measured?
Yeah, so we use this fit here. So if I go back to this
Yeah, I
slide,
think you had a slide on this. Yeah.
yeah. So what we do is we measure the precise line shape of how the thermo current, so the electric current in response to a delta T, how that behaves as a function of gate voltage. That contains a lot of information, and we fit this to our theory. So assuming we need to, for example, know the coupling strength of our quantum dot,
Mm-hmm.
but with that, then we can fit that, and that fit contains the temperature on the hot and the cold side.
Okay.
So we're really heavily relying on this model reproducing physics well.
Yeah.
The reason we trust it is that it does, and the reason it took us 10 years to get there is that in the other dots it didn't.
I
And
see.
with the other theory, yeah, we really
Yeah.
needed to go to higher order theory also.
Yeah. Right. Actually, that's something very interesting that I also learned from your work. I mean, also the theory, sort of from 2010, but the fact that you really need to take into account the broadening of the transmission function, right? So you can't just go to lowest order in the coupling, because otherwise the power
So,
efficiency curves come out wrong. I mean, that was very instructive,
yeah.
I think, for all of us in our group learning about this stuff. Okay, so we have a question from Rafa Sanchez, who says, "What are the advantages of quantum dots built in nanowires? I guess compared to those defined in 2D electron gases?"
I think you can I think you could do equivalent experiments in 2D. There's some advantage that in nanowires we use heterostructures to define the quantum dots, meaning, well, there's an advantage and disadvantage. The advantage is they are set by the crystal structure, and you don't need to worry about gates responding to your voltages, so that there can be sort of crosstalk between gates or crosstalk between your bias voltage and the gate. The disadvantage is, of course, once you have a quantum dot, you cannot tune it. So you're set, you have to choose carefully which quantum dot you use. But I mean, you can do the same experiments, I would say, with 2DECs. The heating challenge is still there to get this local heating to work without heating everything. But I think that can be done. And similar experiments have been done, but not targeting this sort of perfectly tuned efficiency thing.
Okay, thank you very much. Yeah, so maybe I can ask a question. I mean, if anyone else has any questions, please feel free again to just write them in the chat window. But I was interested by this this load matching, which seemed to be very important, right? So you said that in order to get maximum, of course, you always want maximum power, right? So maximum power depended very strongly on the load, and you said that you basically just sort of played around to find the correct load. I mean, is there some prospect of predicting this theoretically? I mean,
yes, actually, I should have mentioned that. So Martin Josephson wrote a follow-up paper, which came out in PRB just in the last 12 months, something like, where he addresses exactly that question. So he came up with approximate equation even. So both a simplified experimental process of finding it, but also an approximate equation that you can actually use to predict it. Yeah,
I see.
It's not as simple as saying it's the same resistance as the quantum dot, because the quantum dot has such massively changing resistance as a function of gate voltage. There is no, it's sort of a self-consistent thing. But nevertheless, Martin was able to come up with a closed approximative expression that you can use. So yes, it exists now.
Okay, great. I'll check that out. Thank you. So we have another question from Janine Schwedstosser, who says, is the main goal of the hot carrier solar cells to increase the efficiency, or would it rather be the output power?
It's what I would say the main goal is the efficiency, to get to higher efficiency without needing to go through the trouble of making a triple junction or double junction solar cell. So you would want to have a simple system that's as simple as a p-n junction in terms of production, but at higher efficiency than you can achieve with a p-n junction. Now, the higher power is sort of assumed there. So, of course, you want both, but people typically would phrase it as higher efficiency at a given power, I would say.
I mean, just generally, I always think of, I mean, in this nanoscale thermoelectrics, I suppose higher efficiency is always kind of what you want, right? Because if nothing else, you can just put many things in parallel to increase the power. No, I mean, that's sort of the picture I always have.
That's right, yeah.
Okay. Great. Thanks very much. So I think that's basically it for the questions. We've had lots of questions, so maybe this is a good moment to conclude. So thanks everybody once again for tuning in, and thank you especially to Professor Heiner Linke for a really interesting talk. Thank you.
Thank you. It was a pleasure and fun. Thanks for listening.